So far in Unit 2, we've covered z-scores and empirical rule. So a z-score is basically how many standard deviations a data point is from the mean. So in number 1, we have Jared, who scored a 73 on a test, and the scores were normally distributed. So basically we know that we can use z-scores for it because it's a normal distribution. Remember, normal distribution just means it's like bell shape, it's symmetric, so basically we know the scores follow like a pattern that looks like that. All right, and it has a mean of 68 and a standard deviation of 3. So we want to find Jared's z-score. So there's a formula I gave in class that the z-score is going to equal the value minus the mean divided by the standard deviation. All right, and in order to find Jared's z-score, notice we are finding it. That means we don't know the z-score. We are finding that part. We know that this will be the variable that's left in the equation. That must mean that we have all the other information to fill in. So if we go ahead and do that, we know that his actual value on the test was a 73. So we know 73 is going to go here. And then the mean is 68. So I know 68 is going to go here. And then standard deviation was 3. So I know 3 is going to go here. So if I set it up that way, I have z is equal to 73 minus 68 divided by 3. And then I can go ahead and just put that in the calculator and see what I get, which gives approximately a z-score of 1.6 repeating, or you could write it like 1.67. That way we're rounding one of the 6's. So basically what this tells us is that Jared scored about 1.6 standard deviations above the mean. So his score was obviously better than the average. We can see that here. We see that, his score 73 was better than the mean, but it's about 1.6 of these above the mean, about 1.6 standard deviations above the mean, since it's positive. So that's our final answer for his z-score. Now, another thing that we did is we said, okay, well, what if you're given the z-score? Could you find the actual value? So problems like this, where we have the distribution of heights for teenage girls is normally distributed with a mean of 62 inches. So we know that's our average, we know that's our mu, and a standard deviation of 2 inches. So we know we have our standard deviation. It says if Leslie's z-score is 2.3, so now it gives you the z. We want to find her actual height. So once again, we're going to use a z-score formula because it sounds like we have pretty much all the ingredients, or most of the ingredients. You basically have to have 3 of the 4 ingredients and you're finding the 4th one. So we know it's value minus the mean, and I'm just going to use letters and so I could shorthand this. So the value minus the mean divided by the standard deviation. So, where'd this extra line come in there? Okay, that's my fraction bar. So we know that the mean is 62. So I know 62 is going to go here. I know that the standard deviation is 2. So I know it's going to go down here. I know the z-score is 2.3. So notice that's going to go here. What we don't know is her actual height. So we don't know the value. That's going to remain v. So it's very important you read and put things in the right place, because a lot of people just assume that we always have the value, and we don't. We need to find the value in this case. So now if I just rewrite what I have 2.3 equals the value that we don't know minus the mean divided by the standard deviation, which is 2. And now we have to get v by itself. So notice in this one, z was already by itself. We were finding z. We already had the value. But in this one, go to the next page, we are looking for the value, so we have to actually solve to get it by itself. It's not already by itself like on the other one. So to do that, we have to do a 2-step equation. It is a 2-step equation algebra problem from here. So if we multiply by 2, we'll be able to get rid of that 2. But whatever we do to one side, we got to do the other. And if we multiply that side by 2, we're going to get 4.6. And I'm just going to bring down everything that's on the right that hasn't not been used yet. All right, so now we have a one-step equation. So now to get v by itself, we have to add 62 to both sides. And now we can see that that will go away. That inverts itself. So v equals, that's 66.6 inches. Oh, wow. Do I have to put it? Okay, so about 66 point, okay, we're going to put it. But we're going to go ahead and say, let's see. So she's about 66.6 inches tall, which is approximately, we're going to change that so our final answer is approximately 67 inches tall. And what's this person's name? Leslie. So Leslie is approximately 67 inches tall. So we'll have that as our final answer. All right. So that is how we use the z-score formula, but to find something else besides the z-score. And then we move on to the empirical rule. So on, I forgot what day, maybe Monday, one of our classes, we discussed how we can make histograms for data. I'm just sketching over here. It has nothing to do with the problem. And if they follow a normal distribution curve, then technically we don't really need the histogram. We could just focus on the curve and how it behaves. So a normal distribution is nice bell-shaped. It has a mean, median, mode all lined up here in the middle. But what the empirical rule says is that if we go out one standard deviation away from the mean, then what we'll do is we'll find, within that range, we'll find 68% of the data will be within one standard deviation of the mean. So that is the empirical rule. I didn't make up that, I didn't calculate that number. I didn't make it up. The empirical rule is kind of like a fact. It says that we will find approximately 68% of the data within one standard deviation to the left and right of the mean. The empirical rule also says if you go out a second standard deviation from the mean on both sides, you will find, so 2 standard deviations away from the mean, you'll find 95% of your data. So we'll find 95, that's almost all of our data. And that's why we only look at going 3 out because that's really almost all the data. So going 3 out to each side, 1, 2, 3 lines, 1, 2, 3 lines, that's 99.7% of the data. That's almost all of it. So what the empirical rule allows us to do, it allows us to break down those percentages further to help solve problems. So like in number 3, or in this problem, we have the average weight of 1-year-old baby boys is approximately, so our average weight is approximately 21 pounds. Notice in these sentences, it's written in English. It's plain language. So you can't expect that the description of what the number is going to be right next to it. Notice the description of what that 21 represents is all the way in front of the sentence because it's kind of introducing what the sentence is about. Sometimes that happens, so don't expect, to number pick and be able to find the word that goes with that number directly next to it. You actually have to read it. So we have the average weight of 1-year-old baby boys is approximately 21 pounds. So we know that the average is 21 pounds, which remember the average is just your mean. So we know that's our mean. And suppose the standard deviation was 3 pounds. So we know that's our standard deviation. We know it's distributed normally. So I know I can make a bell curve to represent this data. So I'm going to make my bell curve. Let me show this really quick. So this right here is just kind of a note that we made in class. This wouldn't be something you'd put on this problem. So I'm just going to put a cloud around it so we know it's kind of just like a side note. It's information we used to solve the problem. All right, so to continue, we have to draw the distribution. So we always put the mean in the middle. And the mean in this problem is 21. 21's our mean, it says it right here. And the standard deviation is 3. So what you're going to do is notice how here I only drew 3 lines out to each side because that's going to capture almost all the data. It's 99.7% of the data. It's almost all the data. So we only need to draw 3 lines out to each side every time, because 3 lines out each side will capture almost all the data. So to get the numbers at the bottom of these lines, we use our standard deviation, which is 3. That is basically like our intervals. That's how much we want to go up and down by each time. So I am going to add 3 to get this next number. So we know that that is 24. I'm going to add 3 again to get the next number. So I know that's 27, and etc. So you want to continuously add 3 when you go to the right, just like a number line, because we're going up by 3. So then we have 30. Let me erase this, because you don't need this part. Alright, so the same way we added 3 to go one way, we would subtract 3 to go this way. So we're going to subtract 3 from 21, and that gives us 18. I don't want to do that in pink. Alright, subtracting 3 again would be 15, subtracting 3 again would be 12. So far we set up the mean in the middle. We added 3 to each side to get the numbers on the ends of these lines and our bottom, and we added or subtracted 3 to go this way. So now, to finish off the curve, we need to put the percentages in there. So the percentages will never change no matter what data you have. You will always put 34% here and here, because based off the empirical rule, notice the middle 2 will add up to 68. Well, 68 divided by 2 gives us 34 and 34. So still, just like I showed in that little cloud over there, this adds up to 68% based off the empirical rule. So that's why the percentages will never change. So whenever you create a curve, no matter what the data is, the problem is about, you're still going to put these same percentages in this section that we're putting here now. So the next section is going to be 13.5. So you'll always use 13.5 in the second sections on each side of the mean. And that is because, just like over here, that those middle 1, 2, 3, 4 sections have to add up to 95%. Well, if you add these up, you will see those add up to the middle 95% of data. All right, and the last sections will always be, not last, but the second to last will always be 2.35%. So 2.35% of the data. And then the very, very last section is 0.15%, not even 1 whole percentage point. So 0.15%. All right, so now we have our actual curve all the way drawn, and now we can answer some questions. So the first question is, what percent of 1-year-old baby boys would we expect to be between 15 and 24? Well, here's a 15, here's a 24. Notice it says between, so these are the lines that we are basically going to use as our cutoffs. So from 15 to 24 is all the percentages within that amount. So you want to add those up, the percentages between the cutoff. Notice we're finding percent. So you're going to add the percentages up and you'll get your answer. And that answer should be 81, try to squeeze it in here, 0.5%. All right, so that answer is 81.5%. So we can expect 81.5% of the baby boys to have weights between 15 and 24 pounds. So 81.5% of baby boys will weigh between 15 and 24 pounds. Now the next question is, what percent would we expect to weigh less than 18 pounds? Well, I'm going to have to undo some of my writing here because otherwise it's going to get crazy. As far as messy up there on that graph. So I'm going to undo it to there. Okay, put my answer back really quick. 81.5%. Okay, so now what percent will we expect to weigh less than 18 pounds? So I'm just going to go to the 18. Less than would be that way. Everything that way. So here's my 18 line. Everything less than that. So that means I need to add up every percent that's below that 18 line. And if you do that, you will get 16%. All right, so basically you just add the percentages if it's asking for percentages. Let me undo so I keep my graph kind of clean up there. So that's 16%. So see, what percent will we expect to weigh more than 27 pounds? So now I'm going to go to the 27-pound line, and more than would be everything greater than it, everything to the where the weights are more than it. So I'm going to add up those two percentages, and I will get 2.5%. All right, actually, let me undo again so my graph won't stay messy. All right, so 2.5%. All right, so for letter D, this is not asking for a percent. Notice it's giving us a percent. So it's asking us over what interval can we find 95% of the 1-year-old boy's weights. Well, so it's kind of backwards. Now it's giving you the percent that you need to find and figure out what numbers, what weights cut that percent off. So remember, here's your percentages. We need to figure out which percentages add up to 95% and then figure out which lines those are related to. So I'm going to just start in the middle here. If I add these two, we get 68. Well, notice if we look at our little graph here, it's kind of a little cheat right now, but if we go out 2 lines over and 2 lines over this way, that middle 4 sections should add up to 95. So let's see if that happens. So if we go over 2 this way and 2 this way and use those lines as our cutoffs, do these add up to 95%? So if you use your calculator, add up those 4, you will see that those add up to 95%. So therefore, the question is, well, what lines are the cutoffs? What is the interval? Well, that is from 15 to 27. So your answer would be written as 15. Whoa, flip the page on myself. Undo. 15 to 27. So that's basically how you would answer that question. It's asking the question backwards. All right, let me undo so my graph won't remain messy, just as I did before. One more. Okay, so we have, what was it? Oh, it was 15 to 27. All right, so for E, it's asking, what weight does a baby boy have to be in the top 15%? Well, if I'm talking about the top 15, then I'm going to start up here, at the top, and I'm going to see what percentage am I going to find, or what sections are going to add up to give me that top 15%. So this is the top 0.15%. If I add this and this, I'm going to get 2.5%, so that would be the top 2.5%. If I add this, this, and this, I will get 16%. So basically, what is the lowest number? Where's the cutoff for this section? Well, if I just sketch it or kind of shade those sections, let me use orange. So if I shade those sections, these are the sections that'll give me 16%. Well, notice that stops right here at this line, and that is our 24 pounds. So we can say, it's just asking what weight does a baby boy have to be in the top 16%. So basically a weight of 24 pounds or more. You don't want to say like 24 to 30, because if you say 24 to 30, that's going to only be this much. It's not going to include that 0.15. But it won't add up to 16 if you just do these two. You have to include that 0.15. So that's why you want to say basically everything from here over. All right, let me undo so it's not so messy. My little lines. All right, so that was 24 pounds or more. All right, what weight cuts off the lower 2.5%? So now we're talking lower. So now I'm going to start the lowest and start adding percentages until I get 2.5%. Well, it won't take you long, because when you add this and you add this, you'll see that together these two sections add up to 2.5%. So this is the cutoff for that lower amount. So that's a weight of 15 pounds. All right. So hopefully that helps you guys understand z-scores and empirical rule if you guys missed anything. And that is it.